Hello, this is Dr. Muhammad, and this is another video under seismic design of structures. Today I'm going to talk about the structural separation, and I'm going to talk about three different points in our example. Mainly I'm going to take an example and I'm going to highlight the different points here that listed in this little contents. So I'm going to talk about the structure separation, the importance of it, and then in the example I'm going to talk about the separation within the same building and the separation from an adjacent building on the same property and separation from an adjacent building on another property. So these are the main three items. On top of that, I'm going to talk about, of course, ASCE 7 seismic provision regarding structure separation, and today I'm going to add ASCE 41 provisions also regarding structure separation because they are a little bit related to one another. Okay, let's go and have an introduction to the structural or the seismic pounding between adjacent building and why the code is trying to put this limitation between the buildings. As you know that there is the phenomenon of seismic pounding. Whenever that we have any two buildings, it is commonly if the distance between the two is not going to be enough or it is going to be small. In this case, any kind of deformation in one of these buildings going to make might happen to make a kind of damage to other structure through what we call it seismic pounding. So in this seismic pounding, because the structures are going to move and to be under the motion of the ground excitation, each structure is going to respond direct or respond in a different way to the seismic ground excitation. So in some cases, there might happen a case where the separation between the building is very small and they are working like out of phase. So sometimes if we are going to talk about what will happen for the structures, if we have the structures like this and they are working or they are going to have their respond to be in motion, or they are going to be in phase, so we are going to find the structure are like moving in this way, for example. So still they are keeping the separation, and also in the opposite way they might work like this. So the structure is going to be like this without any kind of pounding. But the problem comes whenever there is out of phase motion for each or for these two adjacent buildings. So in this case, you are going to find that the lift structure, for example, is moving to the right, and the right structure is moving to the left, and then happens what we call it bounding, or the seismic pounding. The problem is that whenever we have this seismic pounding, sometimes it happens with at different situations. For example, this is one of the worst case scenarios where the floor is going to make seismic pounding with the column. So you can imagine the floor mass and moving with the acceleration, and it is going to pound the structure at this column. The column definitely would not be able to withstand this great energy or this amount of energy that is going to be transferred from this building to this building at the column point. Other cases where we are having the pounding between heavier and lighter buildings, so building like this, the slab or the diaphragm, it is light slab or lighter slab, and here we have heavier slab. So if there is a pounding here, you are going to find this slab is going to make a large or transfer a large amount of energy to this lighter slab building. Also, another case of pounding happen what we call it a pounding between taller and shorter building, as you can see. So the pounding force is going to be at this place here, almost halfway through of the height of the taller building, which might happen. In this case, there might be a kind of mechanism would take place at this level. Another pounding, we call it eccentric pounding. So this is due to the eccentricity of one part of the building. So this means that there might be a kind of pounding here. Another thing, or another case, which is the end building pounding, where that we can find that if we have like set of buildings, the last one might happen to work out of phase, and then it is going to have the pounding at the level. Okay, and of course we know that we have seen that in different earthquakes. As you can see here, for example, this is two buildings and the separation was not enough, so we found that there was a seismic pounding at the roof, and you can find the amount of damage here. Also, it happened here. For this, if we magnify it, you can find that there is a seismic pound happen. So it happens in whatever earthquake, as long as there are structures that is not having sufficient separation between them. Okay. Now let's go to the code and see what the code is writing about the separation and the requirement for structural separation. I'm going to talk about ASCE 7.16 first, and this is actually related to section 12.3.3. And let's go and see what is written there. Under this section 12.12.3, I'm sorry, it is 12.12.3, not 12.3, it is 12.12.3. Okay. So it is written that all portions, they are talking here about the integrity of the structure. So it is written, all portions of the structure shall be designed and constructed to act as an integral unit in resisting seismic forces unless separated structurally by a distance sufficient to avoid damaging contact as set forth in this section. Here the code is setting an important rule or principle that in general we want the structure to be an integral point, means that it should be connected together. However, in resisting the seismic forces. But sometimes we have structures that they are something like this, for example. We need to separate the structures, because whenever that we have earthquake, it might happen that this area is going to be overstressed. So in this case, we want the structure to work as one unit. But if this type of working as one unit is going to add additional stresses at certain parts of the structure, then it's better to separate between the buildings here, or between parts of the building. Okay, so that's an important thing that we want to highlight, or the engineer should take care of, that you need to separate whenever that you think that the integrity or the building having the integral unit, having all the building parts to be together, is going to worsen the situation. Separations shall allow for the maximum inelastic response. This is an important issue. The separation that we're going to talk today about, it should take into consideration maximum and inelastic response. We're not talking about elastic response here. So this is why whenever we are talking about inelastic, this means directly that we are going to multiply and divide by CD over, or multiply by CD and divide by IE, which is the importance factor. The deflection amplification factor over the importance factor times the elastic response or elastic displacement. Okay, and this delta maximum, inelastic maximum, it should be determined at the critical locations. So this is what we have mentioned before, the critical locations. So for example, something like this one, okay, or maybe here, okay, or maybe here at this level. So we need to find this maximum at critical locations. No need, for example, to calculate the maximum inelastic at this level, because we know that it's not the critical one. The critical one is at this level, the third level, for example, here. Okay, so and so on and so forth. So that's the meaning of that delta M shall be determined at critical locations with consideration for translational and torsional. As we said, torsional is going to be taken into consideration. So if we're going to talk about this case, for example, so you need to think about this edge. How much under the torsion, under the amplification of torsion, how much that the inelastic displacement would take place here. Okay. Okay. Of the structure, including torsional amplifications, where applicable, using following equation. And we understand this equation very, very well already. I have explained it 2 or 3 videos back. Okay, and this delta max is the maximum, as we said, elastic displacement at the critical location. So we are going to calculate the maximum elastic, then multiply it by the amplification, deflection amplification factor, and we will divide by IE. And I have explained why we multiply by CD, why we divide by IE in the video related to the drift calculation. So please revisit this video for understanding the meaning of this equation or the rationale of this equation. So after that, the ASCE 716 states that the delta maximum or the buildings should be separated. So the buildings should be separated by a distance. This distance, we call it delta max T or delta MT. Okay, and this delta MT is going to be function of the critical inelastic displacement from building 1 and critical inelastic displacement from building 2. So we're going to use 2 deltas here. The point is delta MT is going to be the square root of sum of the squares. Okay, delta M1 and delta M2 are the maximum inelastic response displacements of the adjacent structures at their adjacent edges. We're talking about adjacent edges, of course. Okay, so that's an important issue. Now the question is why we use this. What is the rationale of this? Square root of sum of squares. Actually, we cannot say anything except that they are considering the linear dependency or the linear relation between the inelastic displacement. That's it. It's a kind of statistical representation for the separation limit. That's what we want. Maybe you can think about that we should get delta M1, for example, and plus delta M2, and that's it. But actually, this is not going to give a statistical representation. This is like a little bit exaggeration here. So we are taking a statistical value, something that is representing both based on square root of sum of squares. And I'm going to talk about this in the commentary of ASCE 716. Okay. Okay. Now there is an exception. Smaller separations or property line setbacks are permitted where justified by rational analysis based on inelastic response to design ground motions. Actually here, as usual, whenever that we are having a very severe or very conservative kind of ruling for some limits that is given by the code, if you are going to work with rational analysis here means that, for example, nonlinear time history analysis or nonlinear static procedure, for example. But I strongly recommend nonlinear time history analysis for this case. Okay, so if we're going to use rational analysis, more rigorous analysis, in this case we can reduce. Okay, smaller separations or property line setbacks are permitted. Okay, we're justified by rational analysis. So do not follow blindly the equations here. If you are having the capability to do or to make or conduct a rational analysis like nonlinear time history analysis for a group or set of earthquakes, then it is allowed for you to reduce the amount of the separation limit. Okay, so this is something common we want. Now the commentary of ASCE 716 on this section, again it's the same, it's 12.12.3 I guess. So the introduction of separation within the structure, typically called seismic joints. We call it seismic joints, as we can see here. It seems that here it is like not following this separation, is not, seems not to be following the right code rulings regarding it. For the purpose of permitting their independent response to earthquake ground motion. We talked about this, that we are seeking for the independent response for certain parts of the structure. Such joints may effectively eliminate irregularities and large force transfers between portions of the building with different dynamic properties. As you can see, maybe we have deformation from building 1 and this is from building 2. They are having different dynamic properties, and of course they are going to respond in a different way to the same ground motion. So in this case, if we take care that if we have any kind of also like piping systems or anything that is related and linking between the structures, we need to take into consideration this kind of movement and the relative movement between the two buildings. In the commentary, they are putting some points. I'm going to go through them quickly. So here, the standard requires the distance to be sufficient to avoid damaging contact under total deflection. Look to this word, total deflection. So it is recommended that the distance to be computed using the square root of the sum of squares of the lateral deflections. So it is only a kind, as I said, the code needs to put a kind of sufficient the standard requires distance to be sufficient to avoid damaging contact. Such a combination method treats the deformation as linearly independent variables, and this is what I want to highlight here. So the square root of sum of squares, okay, it is dealing with that delta m1 squared plus delta m2 squared. It is dealing with them as linearly independent. They are not dependent. Linearly independent variables. Linearly independent variables. And this is true actually, if we're going to say that this is true. There is no relation between the two variables. So this is why we put them as, or we use the square root of sum of squares here. The deflections used are the expected displacement. This word is a key word here, expected. E.g., the anticipated maximum inelastic deflections, including the effects of torsion and diaphragm deformation if we have. Okay, so that's why the word inelastic again repeated here, maximum inelastic. Okay. Just as these displacements increase with height, so the more height that we have, if we have buildings like this, for example, it is different than two buildings like this. The separation here is going to be smaller than the separation here. Why? Because we are talking about the maximum the maximum inelastic displacement for each one. So if it's very high, this means that this distance, which is h, is high, and this requires the displacement and the roof is going to be very high. So this is why if we go back here, it seems to be not following the separation limits. It seems that this building 1 and building 2, they are very tall to the point that this separation seems to be not enough. Okay. The last point in the comments, if the effects of impact can be shown not to be determinantal, means that it will not control, because as we said that there should be a kind of impact between the two. So if we are going to like simulate this impact and we are going to analyze it using FEM, for example, And we found that this impact is not going to make a great deal, okay, on one another. For example, if they are having the same floor masses, that if they are going to collide to one another, if there would be minimum damage, and we do not want, or this kind of effect or impact is not going to be detrimental, means that it will not control our design. In this case, the required separation distances can be reduced. We can reduce it. So it is something important also for you. And this is based on the engineering judgment and decision. There is something important related to the building with rigid shear wall structures. Okay, buildings with rigid shear walls or rigid shear wall structures. The commentary says that for rigid shear wall structures with rigid diaphragms, those lateral deflections cannot be reasonably estimated. That's important. So the code is confessing here that the deflection method that we are going to use in order to get the maximum displacement for rigid shear wall structures, it is not reasonably estimated. Based on this, the NEHRB provisions, which is FEMA 2009A, it is FEMA P 750, suggest that older code requirements for structure separations of at least 1 inch plus ½ inch, 13 millimeter, for each 10 feet of height above 20 feet be followed. This means that if we have a building, for example, okay, and we have it like 2 floors here, so after 6 meters, 2 floors, we are going to count like this: 1 inch, so it is at least 1 inch, plus ½ inch for each 10 feet 30 meter height above the first 6 meter. If we say that the first 2 floors are 6 meters, so if we put another floor here, then we're going to add ½ inch here. If we add another one here, so we're going to add another one here, ½ inch here, and so on and so forth. So this would give us the lateral displacement for the case of rigid shear wall structure. Okay, so that's the meaning here. And of course, if we are having the other structure to be rigid shear wall structure, we are going to apply the same philosophy or the same requirements here. Okay, so remember that if we have rigid shear walls, then we need to follow the older code provisions, not the common way for us to calculate the deflection or the displacement, not CD times delta max over IE. Okay. Okay, now let's go to, we are going to have a quick exposure to ASCE 4117 on section 7.2.13. This is related to the building separation. Actually, we want to know what is the difference between 41, I mean ASCE 7 and ASCE 41. This 41 is for existing, it is for evaluation of existing structures. However, ASCE 7 in general, it is for new buildings. Okay, it is for new building structures. So that's the difference. This is for existing and this is for building. This is for evaluation, mainly for evaluation of existing buildings. This is the like the requirements for new buildings and other structures. Okay, so they are going to be similar in this case, but you're going to find some additional points here in ASCE 41. Let's see what it is telling. First of all, the main idea is the same. In ASCE 41, it also gives the same, that is the delta 1 squared plus delta 2 squared under the square root. They are going to prevent it or prevent pounding by minimum distance, which is SI here at level I, unless they are exempted by specified section. There is some exception, exception here or exemption from this. We're going to look to it. Maybe it will be helpful for us also in the case of existing structures. Okay, First of all, yes, delta 1 here, it is as before. It is the maximum lateral deflection of building 1. It is relative to the ground, because as we said that we are talking about structures, that is the maximum point here, for example, relative to the structure. We are talking here about the absolute total inelastic response. Okay, it's not drift. We are not talking about drift here. Drift, it is for the design and so on, but here we are talking about the absolute total deflection. Okay, it is not related to the story, other stories and so on. It's not a drift, it is total. Okay, relative to the ground. Okay, under the seismic hazard that we are talking, and delta 2, it is the same. There are some additional kind of requirements here, but it is not our scope actually in this course to talk about it, because we are talking mainly about ASCE 7. So we are not going to talk about this, but what I want actually to highlight is this point, which is the exception, because it might happen also for us to think about the exception. Separation exceptions for structural deformation levels of life safety or lower. Generally, this is the performance level that we are designing for, even using ASCE 7. So in ASCE 7, we are designing our structure for life safety limit state. I mean that without realizing that, we are designing for the life safety limit state. Okay, so here he is stipulating that if for existing building, for structural performance levels of life safety or lower, buildings adjacent to structures that have diaphragms located at the same elevation, look to this, located at the same elevation. So this means that the structure is going to have levels. Okay, this is the level, and we have another building that is having the same level of diaphragm, the same level. That's an important issue. So we are going to avoid the pounding of columns. If you remember, in the first slide I was talking about the pounding of columns. Okay, so if structures that have diaphragms located at the same elevation and differ in height by less than 50% of the height of the shorter building, so this means that one of the buildings is higher than another, okay, but not more than 50% of the height. The difference is not more than 50% of the height of the shorter one, okay, of the height of the shorter building, need not, this is the point, need not meet the minimum separation distance specified in section. This is only to keep in your mind. Okay, again, I place emphasis, we are talking about ASCE 41 for existing building, and this is for the evaluation, but only I want to highlight this point, that there is an exception there if you want for existing buildings. Okay, and again, even for new buildings, if you could, using rational analysis or by an expert engineer, going to tell that the effect of seismic pounding is not that much, then in this case you can reduce the amount, or even you can eliminate it if you are sure of the effect of seismic pound, that seismic pounding would not make a unfavorable consequences. Where an approved analysis procedure that accounts for the change in dynamic response of structures caused by impact, that's the point. If we could make the impact analysis is used, the evaluated and retrofitted buildings need not to meet the minimum separation. So because we're talking about evaluated and retrofitted building. This is for evaluation of existing structures and retrofitting of existing structure. So the evaluated and retrofitted building need not to meet minimum separation distance specified in the section that we have explained before. Such an analysis shall demonstrate that. So what is the type of analysis? We have two analyses here. The structure are capable of transferring forces resulting from impact for diaphragm located at the same elevation, which is this, there is impact here would take place and no problem with this. And number 2, the structure are capable of resisting all required vertical and lateral forces considering the loss of any elements or components damaged by impact of structure. If there is impact and there are some elements that is going to be damaged based on your analysis, and you find that it will not make a great or it will not make a mechanism, for example, then it is okay for you. Okay? So again, this is really important to be given by an expert engineer. Okay, now this is the commentary of ASCE. 2 points only I want to highlight quickly, and then we can go to the example. So this standard permits retrofitting building, we are talking about retrofitted building here, okay, to experience pounding as long as the effects are adequately considered by analysis methods that account for transfer of amount of momentum and energy between the structures. As we said, this can be, if you could like make the analysis, then do it. Approximate methods of accounting of these effects can be obtained by performing nonlinear response history analysis. Do you remember that even in ASCE we were talking about rational analysis? That's what we want, nonlinear time history analysis. Okay. And also there are, like as they are stipulating here, saying that approximate elastic methods for evaluating these effects have also been developed and are presented in literature in 1990. Means that elastic methods are available and you can go and see this paper if you want to go through this. Okay, now it's the time for us to go to the example. And the example of today, we are going to use 2012 IPC SAIC Structural Seismic Design Manual, and actually it follows ASCE 710, so we are going to go through it. Okay, now let's go with this here, the design example. It is structure separation, and the item that we are talking about, sorry for this, this is not here. Okay, so the section that is under consideration in ASCE, it is 12.12.3. So structural separation are necessary to prevent or reduce possibility of two adjacent structures impacting during an earthquake. Requirements for structure separation are given in the section 12.12.3. Now let's go to the problem statement that we are going to have here. In this example, the static displacement delta XE, take care, we are talking about elastic here, due to the prescribed lateral forces of section 12.8, which is ELF, equivalent lateral force method, and information about each structure are given below. Note that displacement given are at the plan view edges of the building. So let's see what is being given here. This is at the plan edges of the building. So we have two buildings, as you can see. One building is 3 floors, the other one is 2 floors. One, as you can see, seemingly to be like moment frame, the other one is braced frame. So structure 1, 3 floors, structure 2, 2 floors, and there is a separation here. We have conducted the analysis, which is seemingly to be elastic analysis, and we found that we have at the floor level, which is at the ground level, the deformation is 0 as expected. For structure number 1, we have the first, second, and third levels. They are having these values, 0.47, 1, and 1.38. Of course, whenever that we go higher, we are expecting higher values of the elastic displacement. Similarly, for structure number 2, we have 0, 1, 2, and there is no 3 here. There is no third floor. So we are having the same, similar, or the delta XE is 0.35 and 0.75 respectively. Each structure, it has its own response modification factor and displacement modification factor, amplification factor. So here it's 8, here it's 6, CD here is 5.5, here it is 5. So we want to determine the following. Number one, the separation within the same building. If these two parts are parts from the same building, so what will be the separation? And number two, separation from an adjacent building on the same property. Consider them that they are like two different buildings but within the same property. And the third case is the separation from an adjacent building on another property, that as if that this building does not belong to the property of the first building, for example. So we need to know how to go through this example. Let's go. First one is that separation within the same building. Separation within the same building. So we are going to work with the same equation that is given by section 12.12.3, and this is the equation 12.12-2, okay? So which is the square root of sum of squares. Okay? So joints are often used to break larger buildings or an irregular building into two or more parts above the foundation level. This effectively creates separate structures within the same building. The code requires that the structure be separated by amount of this delta MT. So we want to know what is delta M1 and what is delta M2 that we are going to use. Actually, this delta M1 and delta M2, it is, as we said, maximum inelastic for both, for structure 1 and structure 2. Already we, after having this maximum inelastic, which is going to be obtained by the elastic or from the elastic displacement, so it will be, this is the elastic displacement multiplied by CD and the importance factor. Then we are going to choose this from our table. So if structures 1 and 2 are independent portion of a large building, means that they are within the same building, the required separation is determined in the following steps. We have step 1, step 2, or step A and step B. Determine inelastic displacement of each structure. So we're going to look to what is the maximum, okay, the maximum displacement for each structure. To determine the minimum separation between parts of the same building that are separated by expansion joint, the maximum inelastic floor displacement delta X must be determined for each structure. These are at level 2. Okay, so for structure 1 and structure 2, if we go back, we're going to find at level 2 we are having the maximum here, because really this is the maximum for structure 2, and this is not the maximum for structure 1. It is one of the values, but it is the value corresponding for structure 2. So we are expecting this to be the 2 points or the 2 displacements to be used. Okay, so this is delta 1 here, and this is delta 2 if we're going to talk about the elastic values. Okay, again, why we choose them? Because as we said, if this building, structure 2, is having something here, we will choose it with this one because they are higher. They are going to be under the square root of under the radical. So we are going to, we want to get the minimum separation. The minimum separation is going to be obtained by the maximum value coming from the 2 structures. Okay. So now we have obtained, this is delta 2-1 at floor level number 2, and this is 1 here, and it is 0.75 for the other structure. Let's go back here. It is 1 for structure 1 and 0.75 for structure 2. So we are right here. We calculate this using the equation, and we find this is 5.5 and this is 3.75. Then the required separation is going to be the sum of square roots of the both, which is 6.65. Okay. The next is the separation from an adjacent building on the same property. The code does not give any kind of difference whether the building, whether the 2 parts of the structures, they are within the same property or they are from different properties. The code does not give any code makes no distinction between an internal structure separation in the same building and the separation required between two adjacent buildings on the same property. So our delta M, or the separation, is going to be the same as before. We will not calculate anything. Okay, this is the second one. And the third is the separation from an adjacent building on another property. Whenever that we have a building, okay, and we have another building here, if structure 1 is a building under design, so we have, this is structure 1, which is the taller one, and this is structure 2, and this is in under our design. However, structure 2 is not under our design, it is like an other property. We do not have any idea about it, so we do not know how much even what is the system and how much the displacement. So in this case, the largest elastic displacement of structure 1 needs to be used, and regardless of this value of the structure 2. So in this case, we are going to use the largest one, which is at the roof here. Even that we know that this structure is shorter, but again, we do not have any information from this building, and we will not include it in our deformation. So we're going to get what is the maximum delta at the roof, which is delta 3, 1.38, and we are going to amplify it. So it is going to give us 7.59. Okay, so now there is no square root of sum of squares. We do not know anything about this building. Okay, so put it aside, just you obtain what is the maximum inelastic displacement of structure 1. Okay, so structure 1 must be placed 7.59 inches away from the property line. If we have the property line here, so if we have, for example, this is structure 2, this is a plan view, and this is like structure 1, so, and this is the property line, and this is the case, this one supposedly to be 7.59. Okay, that's it. And the comment here, that is only a kind of little comment here for this. ASCE 7 section 12.12.3 was revised for the 2010 edition to include structure separation based on a square root of sum of squares formulation for structure on the same property. So this is actually, we can consider it, it's new for 2010. Before that it was maybe not the same like requirement. Okay, thank you. This is the end of this video. I hope that you have understood it, and I hope to see you soon in another video. Thank you, and see you.